Hello everyone, my name is Corrado Pezzato. I am part of the Cognitive Robotics Department at the Technical University of Delft in the Netherlands. This video presents our work on adaptive control for robot manipulators through active inference. Before diving into the presentation, I would like to thank the institutions that allowed all of this, in particular the Systems and Control and Cognitive Robotics departments at the TU Delft, as well as Ahold Heese, which partially supported this work within ERLab Delft. First of all, why do we seek for adaptive controllers for robot manipulators in the first place? The first industrial manipulators were used in pretty structured and safe environments, surrounded by big fences. The robots had to perform always the same task with very little variations and were provided with an accurate model for control. In recent approaches, robot manipulators are being applied in more dynamic environments. Here, the work cell has to be flexible enough to handle different packages which can have different shapes, weights, etc. More cutting-edge and future applications are trying to increment the cooperation between humans and robots, which are now sharing the same workspace. And as you can imagine, in situations like these, we cannot provide anymore an accurate model for control. Thus, we need more controllers that can adapt to large uncertainties. Thinking about the manipulation task from the perspective of a human, you can realize that we rarely have an accurate model of what we're handling, yet we can achieve amazing motions. In our work, we took inspiration from a neuroscientific theory proposed by Carl Friston called active inference. This theory tries to explain how our brain might function in terms of both perception and actions, capturing the adaptability skills of humans. The promises are that we can derive a control scheme which avoids the use of accurate models and which is also adaptive against large uncertainties. However, when we started this study, the published work on active inference for robotics was really limited. The main problems of past solutions were that active inference was too computationally expensive and had poor performance. But we will see how with our work we overcame these limitations. Since active inference is a fairly new concept in the field of robotics, I'm going to describe its working principle to have a common ground and understanding. Let us assume that we have a real process that we want to control, let's say a robot arm. This robot arm can be represented by a number of states, x. To control the robot, we have of course our active inference controller, which can sense some noisy quantities from the real process through the sensor input. The controller also represents the real process with a pretty rough model. In particular, it has an internal representation, so an internal belief mu, about the real states x. The controller also encodes two generative models. In particular, the first one, g, explains the relation between y and mu, and the second one, f, represents the belief about the evolution of the states. Furthermore, the controller can apply some control actions to the robot arm, torques for example. Doing so, it can change the sensor input in order to match a desired sensation. As a recap, the controller uses the sensor input together with G and F to refine its internal beliefs, and the controller uses actions to match a specific desired sensor input. Going a bit more in details, how do we update the beliefs and how do we compute the control actions? Well, the belief update and the control actions are computed through the minimization of one single function, the so-called free energy, using a gradient descent. The controller can suppress the free energy by changing the two things it depends on. It can change its internal beliefs about the external states, so performing filtering and state estimation, or it can change sensor input by acting on the environment, using the control actions. So to be able to compute the beliefs and actions updates, we have to specify the relation between the states and sensor input, so G, but also the expected evolution of the states, F, and the effects of the control actions on the sensor input. In our work, we formulate the first active inference controller for online closed-loop joint space control of industrial robots using torque commands. We impose the states to be controlled as the joint positions, so G of mu is simply mu. Also, we use low-level torque commands for each joint. To define our active inference controller, we had to make several design choices to define the expected evolution of the states, F, and the effects of actions into the sensor input. But the key point here was really to keep it simple. So instead of modeling the true dynamics through F, we impose that the states should evolve as a first-order linear system which converges to a desired value mu d. To compute the control actions, we have to specify the two partial derivatives which represent the effect of a torque on measured position and velocity. Possible ways of doing so are deriving the dynamic equations, but this would defeat the purpose of our study, or we could learn the dynamics, but as we saw in past work, this requires a lot of data and can produce unreliable results. Finally, we could approximate the dynamics, relying on the high adaptability of active inference. This was the way we chose to pursue. The approximation we introduced was to only encode the sign of the full time-varying relation. This means basically that a positive torque leads to a positive acceleration. Using active inference, we then derived a model-free control law where instead of modeling the true and no dynamical process, we define a reference model that active inference has to follow. To evaluate the performance of our active inference scheme, we chose a model reference adaptive controller as benchmark, due to its similar characteristics. In particular, also the MRAC does not require a dynamical model of the plant to be controlled. For the tests, we use a Franca Amica Panda 7 degrees of freedom robotar. Basically, the active inference and MRAC are tuned in simulation using a heavily approximated model, with fairly wrong links masses and inertias. Then, the controllers are directly applied to the real robot to appreciate their adaptive properties. First of all, we would like to point out that the active inference controller could be transferred from simulation to real robot without retuning, while MRAC causes a safety stop. We can see, however, some oscillations for the second last joint of the robot, but these are at the end, damping it down. After retuning on the real robot, we use both controllers in a pick-and-play scenario in case of an empty and a full bottle of water. In general, we can see that the active inference controller has a smoother response, which causes less oscillations in the handled object. And this can also be appreciated looking at one cycle in joint space, where the active inference controller achieves the set point in both a faster and a smoother manner. And this brings us to the discussion section. The active inference controller resulted in a very adaptive and yet compliant robot, which is also easier to tune, having less tuning parameters. In fact, the active inference controller has only 6 compared to the 119 of the MRAC. Besides, the control scheme is computationally inexpensive. We were able to provide the control torques within a hard real-time constraint of 300 microseconds using just a standard laptop. However, a formal stability proof for the algorithm is still missing. To conclude, the main contributions of this work and take-home concepts are that, first of all, we confirm the value of active inference for adaptive control, providing experimental evidence. Doing so, we derived the first active inference scheme for online closed-loop torque control of robot manipulators. This scheme is model-free, easy to tune, and computationally lightweight. Besides, its adaptive properties allow it also to transfer from simulation to real setup without retuning. In all the tests we did, we outperformed the benchmark MRAC. However, as we told you before, even if we have a strong evidence of stability of our active inference controller, a formal mathematical proof is still missing and will be part of future work. This concludes the presentation, so thank you very much for your attention. I will be happy to answer any question you might have.